Hello, today we're going to talk about ionic bonding. So we just went over oxidation state and how an atom wants to have a full octet in order to be its most stable form. And so this is going to then translate to ionic bonding, where we have the transfer of an electron. So one thing is positive and one is negative, and then we get attraction. All right, so in an ionic compound, we have positive ions and we have negative ions, and we always write the formula as the ratio of those two things as a 1-to-1 ratio. Although what we actually will get is a lattice of bonds. So you can see like each of these purple atoms or ions is a positive or cation, and it will be attracted to a negative anion, which is the green ones. And so we get a whole network of these bonds, but we just represent the formula as the ratio of how many of the positive to how many of the negative. And the positive ion or the cation always goes first. All right, and because of this structure, ionic compounds have particular properties. They have very high melting points because of that network of bonds, and they also, because of the charges, which we'll learn a little bit more about in the next chapter, tend to dissolve in water pretty easily. All right, so now let's talk about how we write the formula. So in order to have a compound, we need to have a balance of charges. So the first thing we're going to have to do is figure out what charge is each of the atoms in the compound going to have. So potassium, for example, is in our first column, column 1A, all right, which means it has one valence electron, which is going to give away. So it will have a +1 charge. All right, and then oxygen is in column 6A, so it needs 2 more electrons to get that full octet, so it will have a -2 charge. All right, and now the new part here is to make a compound with these two, we're going to need 2 potassiums for every oxygen because we need an equal number of positive charges and negative charges. So since each oxygen comes with 2 negative charges, we'll need 2 potassiums to make it neutral. All right, so magnesium is in column 2A, has 2 valence electrons, which it will give away. Right, and nitrogen is in column 5A, so it needs 3 more to get to 8. Okay. Now this one is a little bit more complicated because if we just had 1 of each, it's not going to be neutral, and we can't just have 2 of one and 1 of the other. It doesn't work. So in math, we call this the least common multiple. So the least common multiple of 2 and 3 is going to be 6. That's the lowest number we can get that both of those numbers would go into. All right, so in order to get to 6 charges for each, we'll need 3 magnesiums to bring us to 6 positive charges, and we'll need 2 nitrogens to bring us to 6 negative charges. So our formula for that will be Mg3N2. Right, so that means 3 magnesiums and 2 nitrogens. All right, the next two I'm just going to go through a little more quickly, but you might want to pause here and see if you can do them on your own and make sure that this is all making sense. Okay, so barium has 2 valence electrons, it'll be +2. Sulfur has 6, so it needs 2 more. All right, those are the same charge, so we'll just need 1 of each in order to get a neutral. All right, sodium is in the first column, it's going to be +1. Fluorine is in column 7, so it will need 1 more. All right, and those have the same charge, so it'll just be NaF. All right, so now how would we name these compounds? So the first element in the formula, like I said, is the cation. That's always the metal, right? So that's going to be everything from the metalloids all the way this way. So most of the periodic table is metals. Anything over on this side is going to be a metal, and it would go first, and its name does not change. All right, so you just take whatever the name of the metal is. That is the name of your cation. For the non-metal, which is the one that comes second in the formula, you're going to change the ending to IDE. So chlorine, for example, is our anion here, and the name of the anion itself is going to be changed to chloride, right? And that will be the name of our ionic compound. Okay, so let's do a couple of these. So K is potassium. That name is going to stay the same, and then we just did Cl before, so that's chlorine, but it will change to chloride. Okay, so potassium chloride. Na is sodium, and then N is nitrogen, and that will change to nitride. All right, and you'll get more used to how the endings change when it's a word that's, you know, nitrogen. It's hard to determine where exactly you cut it off and end the "ide," but it'll become more familiar, I promise. Okay, so then we have aluminum. That's our metal. That name doesn't change. Fluorine is our nonmetal or our anion, and it will become fluoride. All right, so now we've looked at how to do metals that are basically in the first two columns, okay? Those we know the charge of. Unfortunately, everything in the middle section here, and even the metals over here, kind of under the metalloids, those all can have multiple charges, and so we use a system with Roman numerals to specify what the charge is going to be. So chromium, for example, if it's +2, we put a Roman numeral 2. If it's +3, we put a Roman numeral 3. Okay? There are 3 exceptions to this, all right? So we already know group 1A and 2A aren't, we don't use Roman numerals for those, but there are also 3 other metals. So we have zinc and cadmium are always +2, and silver is always +1. So those 3 elements don't get Roman numerals when we name them. All right, so now let's do just a couple of examples of how this works. Okay, so if we have Cu2 and O, we know that oxygen is going to be -2 always. All right, so if we have 2 coppers to neutralize that 1 -2, that must mean each copper is +1. All right, so this would be copper 1 oxide. All right, if we have chromium paired with 1 sulfide ion, that's a -2, so the chromium must have a +2 in order to neutralize it, so it'd be chromium 2 sulfide. Silver, we know, is always +1, so we don't need a Roman numeral for that one, so it's just going to be silver chloride. And then Sn is tin. All right, if we have 2 oxygens, that means that's -4 altogether, right? So 2 -2s makes 4 negatives, all right, which means the tin must have a +4, so that would be tin 4 oxide. Okay, so just a refresher on Roman numerals in case you don't remember them. 1 and 2 and 3 are just I's, 1, 2, or 3 of them. The Roman numeral 5 is the V, and if we have 1 less than that, we put an I before it, so that means 5 minus 1 is 4. This is why I don't use Roman numerals very much anymore. All right, so now we'll do the opposite. So when we have a Roman numeral in our name, we just go back from, you know, the charge that it has. So it's given as a 3 here. That means the iron has a +3 charge in our compound. All right, chloride is in column 7A, so we know it has 7 valence electrons. It wants 1 more, so it's going to have a -1 charge. Right, so then we'll need 3 of those chlorines to balance out the 1 iron. So that'll just be FeCl3. Okay, aluminum is in column 3A, so it's +3 always. Oxide is always -2, and this is one of those ones where we need that least common multiple, so we'll need 2 aluminums and 3 oxygens. All right. Polyatomic ions. So this is one more way that ions show up in ionic compounds. So basically, the atoms in the ion are held together with covalent bonds, which we'll talk about in the next lesson, and the whole thing has a charge. So you just treat this as one unit when you're making the formula. And for this test, you do need to learn these polyatomic ions, right? So the 4 that are listed here are kind of orphans. They don't have a particular pattern. You just have to learn them. I really highly recommend flashcards for this, okay? And then after that, I've grouped them based on sort of a similar base atom. So all of the ones in this group have nitrogen as theirs, right? And the element or the polyatomic ion to focus on is the one that ends in 8, because all of the other ones follow from that with a pattern. So whatever your nitrate or whatever your 8 polyatomic ion is, if we switch from 8 to 8, all we do is take away an oxygen. So if we look at chlorate versus chlorite, it's just 1 less oxygen. Sulfate versus sulfite, 1 less oxygen. All right? Phosphate versus phosphite, just 1 less oxygen. Okay? If we add per to the 8, then we add an oxygen. And if we add hypo, this hypo goes with the ite, then we take away an additional oxygen, okay? Adding hydrogen in the front puts an H in the front, and then also adds 1 to the charge. So when we went from sulfate to hydrogen sulfate, we went from -2 to -1. All right, same thing going from carbonate to hydrogen carbonate, all right, which is also called bicarbonate. And then from phosphate to hydrogen phosphate to dihydrogen phosphate. Again, the charge goes up by 1 each time, and we add a hydrogen each time. Okay, so this will take some effort, and I understand that, but unfortunately, it's one of those few times that I require you to memorize something, because when we get to net ionic equations in a couple of units, if you don't know the polyatomic ions, or at least recognize them as polyatomic ions, you're going to have a lot of trouble. So go ahead and make yourself some flashcards. I like to color code them, so like maybe all the nitrate ones are blue, maybe all of the sulfate ones are, you know, pink, whatever. All right, now we're going to go ahead and just do a couple of examples. So just like before, when you have the names, you need to find what the ion is and the charge. So aluminum will be +3. Bicarbonate is on that table that we just made. And so also a clue that you have a polyatomic ion is the ending doesn't have "ide," right? Ide is specifically if you have one non-metal making an anion. So bicarbonate's a polyatomic ion. It's HCO3 and it has a -1 charge. So we're going to need 3 of them in order to neutralize the aluminum. Sodium is +1. Sulfate is SO4 with a 2-. So we will need 2 sodiums to neutralize the sulfate. Okay. You'll also notice I put parentheses around the polyatomic ion if there is more than one. If there's only one of them, it doesn't need any parentheses. All right. Here we have calcium, which is +2, and carbonate, CO3 2-. So this is just going to be calcium carbonate for the name. Oh, that one popped up first. All right. So that one's calcium carbonate. And then the last one here is copper nitrate. So we have our copper and we have the nitrate, which is -1. All right. If we only have 1 copper, it must be +1. So that's where the 1 here comes from.